In this section, we're going to talk about electrification. This is a follow-up to magnetism and electrostatics. The video is covering magnetism and electrostatics. Let's go ahead and get into electrification. Remember, we say an object, a material is electrified anytime there's an excess or deficiency of electrons on the surface of a solid, or anytime there's a deficiency or gain of electrons in a liquid or a gas. We say the material is electrified. There's three ways you can electrify something. By friction. A good example of that is anytime you shuffle across the carpet with your socks on, you rub electrons from the carpet to your socks, or vice versa. You do the same thing when you rub a balloon on your hair, for example, or remove clothes from the dryer. You notice they've built up electric charge. Sometimes clothes stick together. That's friction doing the electrification. Other methods include just contact. You take an electrically something with a potential difference, like a battery, and connect a conductor from one end of the battery, the negative end to the positive end, and you'll have electrified the conductor. The conductor will allow electricity to flow across it, along its surface. The other is induction. Induction involves, as it implies, inducing electric current in a material by way of using the magnetic field created by a nearby electric source. We'll talk about that in a little more depth. So yeah, with friction, for example, so we'll go through these in step by step. In friction, electrons can be rubbed off of some materials with very loosely bound electrons onto certain other materials, even though neither material was charged to begin with. You're creating a charge. You're using the friction force to create a charge. Both materials are electrified. Whatever you remove the electrons from will gain a positive charge, and whatever gains those electrons gains a net negative charge. Both are electrified. Friction can do things like in radiography cause sudden discharges of electricity. Friction does cause sudden discharges of electricity, and it was an old problem with old X-ray film, sliding it across countertops, out of cassette bins. The film is easy to electrify. Discharges could cause static electricity artifacts, such as these tree static marks seen on this chest radiograph. How do you prevent static discharge? Well, for one, an insulator. You'll notice that you you wear socks with your shoes. You can create friction discharges when you electrify your body, or when you shuffle around on the carpet with socks on. But you'll notice when you put your shoes on in the house with rubber soles, that doesn't happen. So an insulator will do that. It will shield you from a static discharge. Dielectric or insulator materials include rubber, plastic, or oil placed around wires. Grounding something would also prevent discharge. It doesn't prevent the discharge, it just gives a path of least resistance for the electricity to travel. So in a structure, you'll have something like a ground rod, which is drilled or hammered or put deep into the ground, so that if the structure, if for example, is electrified, the charge travels through the path of least resistance to the ground, rather than through conductors in the wall and burn wires and ruin electric circuits and things like that. Humidity as well. Water molecules are bipolar, positive on one side, negative on the other. They tend to attach to charged surfaces, neutralizing any static electric charge there. Humidity above 40% minimizes static electric charge, but less than that, and the dry air leads to the possibility for a static electric charge. Electrification by contact or conduction is occurring when a potential difference exists between two objects. That is to say, there is a difference in charge from one object to the next, like when you have a battery connected to a wire conductor, right? The battery serves as the source of potential difference, the source of potential energy. You have a charge on one side of the battery greater than the other side. Your batteries die when they run out of charge. Any difference in charge is also a difference in potential energy. You notice that, at least with the older style batteries, our lithium ion don't necessarily do this, but in an older style battery, old Duracell AA's, or in your regular old batteries, you'll note alkaline batteries, you'll notice that when they discharge, they tend to decrease in their output over time. They don't just work well, work well, work well, and then die. They sort of diminish over time. If you had it in a flashlight, you would notice the flashlight was less and less bright each time you used it, till eventually it just doesn't work anymore. The potential difference in charge from one end of a battery, for example, to the other, is what causes electrons to move. A high positive charge on one end of a circuit will draw electrons towards it the same way that a large negative charge will push electrons away from that source. Excess electrons will always flow toward surfaces that are relatively more positive. So it doesn't matter if you make one side of the potential difference more positive or the other side more negative. It's just that the relative difference, if that exists and how large it is, will tell you the amount of charge and how much force will be exerted, can be exerted. So yeah, we call this an electromotive force, the force created by any electric potential difference. You get a push or pull by a relative difference in charge from one end of a circuit to the other, and that charge causes electrons to move, so we call it an electromotive force. Electro for electrons moving or electricity, motive for motion, and it is a force. Forces act on things. The unit that we use is the volt. You should be familiar that for example, your car battery is a 12-volt battery. Your homes, you access 110 volts when you plug into the wall, 220 volts when you plug into for example, where your electric dryers plug in. So voltage is an amount of force. I like to describe it as a push or pressure pushing the electrons through the conductor, through the material. Electrification by contact conduction. In order to distance themselves from each other, electrons will always spread out evenly across the surface of two objects in contact. Recall that electrons repel each other, so they'll try to spread out equally. This results in an equalization of charge at the lowest possible value on the two objects if they are then separated. In the next slide, you'll see examples of this. Note that even when one of the objects is neutral or uncharged, there's still a relative difference in charge from object to object, so you still have electrification. For example, in A, you have two materials, one with a -6 charge and the other with a +2 charge, and they will discharge to -2 and -2. 4 electrons move from the X with -6 to the Y with +2. In the case of B, a charge of -6 on X and a charge of 0 neutral on the other will cause electrons to flow from X to Y to neutralize the charge. You'll notice that all of these start with a difference in charge, and it doesn't matter if it's positive or negative charge. Both conductors have a difference in charge. One of them can have no charge, the other can have a negative charge or a positive. The other can or they can have negative and both positive charge, but either way, when you look at the outcome to each, they equilibrate, they equalize, and that's the case. When you have a charged battery, you have, for example, more electrons on the negative side of the battery, giving you a pushing the electrons through the conductor when you connect the wire from one end to the other. And the battery is said to be dead when no potential difference exists from one end to the other, from negative to positive side of the battery. Electrons flow from the negative side of the battery toward the positive side, and they stop flowing when there's an equal charge on either side. There's no potential difference any longer. The electrons will stop flowing, and then we say the battery is dead when that's the case. Lastly, electrification by induction. Induction just induces a charge in a nearby object without actually touching it. This should be no surprise to you, because you learned in previous lectures that objects Electric charges in motion generate a magnetic field. The magnetic field can affect a nearby conductor. And so this is what we're talking about here. A neutral object will become electrically polarized when a charged object is brought near and attracts the object opposite charge towards it. If an object is grounded while it's being polarized, the accumulated charge on that end of the object will flow out or in, leaving the object charged as a whole after separation from the ground.